Hello students. So the today's topic is the third colligative property. Okay, so already the first two I have explained you. The third one is the depression in freezing point temperature. Okay, and which is represented by delta TF. Okay, so depression in freezing point temperature is represented by delta TF. Okay, now what is the first of all, what is the freezing point of any liquid? Okay, so the freezing point of any liquid is that temperature at which the liquid begins to freeze, right? At which it begins to the liquid begins to solidify, right? That is the freezing point temperature of any liquid. Or what you can say, it is that temperature at which your solid begins to melt. Okay, so both things can happen. Either your liquid, when your liquid starts to solidify, or your solid starts to melt, that particular temperature is known as the freezing point temperature of your solution. Okay, so now see what will happen at this temperature. What will happen, since you are saying that the this what to say, the liquid is trying to solidify, right? That is trying to change to the solid phase, right, from the liquid phase, and the solid is trying to melt to the liquid phase, right? So you can see an equilibrium exists between the two, right? And this equilibrium, at this this is the at this equilibrium, that is the temperature is known as the freezing point temperature. Okay, and at this equilibrium, what happens, the vapor pressure of both liquid and the solid are equal. Okay, so in other words, you can also say that the freezing point temperature is that temperature at which the vapor pressure of your liquid and the solid will be equal. And one more thing, you know that solid has negligible vapor pressure, right? Already I have told you. So what you can say that solid has a zero vapor pressure, and hence the liquid has to what, change to the zero vapor pressure, or it has to equalize, right? So at that temperature where the vapor pressure of both the solid and the liquid is equal is your freezing point temperature of the solution. Now what happens whenever you take a say again we will take that you will take a pure solvent, and in another beaker you will take the solution. That means the solute plus solvent. Okay, so what will happen here, whatever freezing point will be there, say the freezing point will be represented by TF naught, because this is for the pure solvent. Okay, and the freezing point for the solution will be TF, represented by TF. Okay, F is for freezing. Okay, so and this is for the solution, this. Okay, so what will happen, what do we see is that as soon as we add solute molecules to the solution, sorry, the solvent, pure solvent, what happens, the freezing point temperature gets decreases. Okay, that means TF is smaller than TF naught. Okay, so that means what we can say is, what we can say is that if we want to find out the change in freezing point, or which is also known as the depression in freezing, because the freezing point is decreasing, right? I already have said you, from beaker 1 to beaker 2 the freezing point is decreasing as soon as you are adding the solute. So we will say that the change in freezing point, or the depression in freezing point, or sometimes they say the lowering in vapor freezing point, will be represented as delta TF, and delta TF will be equal to what, TF naught, which is the freezing point for the pure solvent, and TF minus TF, sorry, minus TF, which is the freezing point for the solution. Okay, like this. So this is one expression. So this is your expression for the depression in freezing point, which is represented by delta TF. So here it is shown in the graph. You can see that this is the solid phase, right? And as soon as if you are saying freezing, that means the liquid has to solidify. So this is the curve for the pure solvent, this is the curve for the solution. You can see since the vapor pressure is decreasing for the solution, you can see the curve of solution is lower than that of the curve of solvent, and this is the freezing point temperature for the solvent, right, pure, and this is the freezing point temperature of the solution. So you can see at this in this line, what you can see in this x-axis, what you can see, TF is smaller than TF naught. So from this graph also it is clear that as soon as you add the solute to the pure solvent molecule, your freezing point gets decreases. Okay, and the change is represented by delta TF. This change is represented by delta TF, which is the depression in freezing point. Now what you can see is, now I'll tell you why. You see, here I have shown you. You see, if you are telling freezing, that means you are trying to, like, from liquid you are trying to change to the solid phase. That means what? In liquid you have some random arrangement, but in solid you have I mean the arrangement is proper. It is, there is no randomness, right? So what will happen, as soon as you are trying to change from the liquid state to the solid state, you are trying to convert to a highly ordered structure, right? The molecules in the liquids, they are not so ordered, right? They are random, but you are trying to make it a order arrangement. So when you try, when the solute molecule will be there in the, that means in the solution, when the solute molecules will be there along with the solvent molecule, you can see I have represented here the solvent. I've just marked here solvent, and these circles, they are the solute molecules. So you can see for a highly ordered arrangement, since we are converting to the solid phase, okay, so what will happen, these solute molecules, whatever is present, okay, so they will just restrict the arrangement. Okay, because of the presence of the solute molecules in the solution, what will happen, whatever we want to prepare, that means we are trying to freeze, so in the solid state, the solute molecules, what they will do, they will restrict their way. Okay, so the arrangement which we want in the solid state will not form easily, right, because of the presence of the solute molecules in between the solvent molecules. So solvent molecules के बीच में जो बॉन्ड बनना चाहिए, सॉलिड होने के लिए जो बॉन्ड बनना चाहिए सॉल्वेंट मॉलिक्यूल्स के बीच में, that will be restricted due to the presence of the solute molecules. Okay, that means the solute molecules will hinder. So for doing such like for solidifying this liquid, what we have to do is we have to decrease the temperature more. Okay, we have to remove the energy of the system, because we are trying to solidify it, we are trying to make it a minimum energy system. So we have to take out more energy from the system. That means we have to freeze the solution more, we have to decrease the temperature more, and hence in the case of solution, what happens, the freezing points get decreases. Sometimes it may go to -1 degree or -2 degrees, such, because pure water, it freezes at 0 degree Celsius. Okay, and as soon as you add some solute molecules, your freezing point is going to dip. It may be -1, -2, like that, because of this presence of the solute molecule. So like this you can understand why it happens, so that when we add the solute molecule, the freezing point gets decreases. Okay, because of the presence of the solute molecule, the solid whatever is to form, okay, that is not formed very easily. So we have to decrease the temperature more. Okay, and hence the depression in the freezing point we see. So here you can see I have shown you. So an example of antifreeze solution is used in radiators of cars. Okay, so what is that? Ethylene glycol and water, you can see. So as if we take water, okay, in normally in car radiators, if we take water, okay, in winters, say the places where there is very cool, the places where there is very like the temperature are very very low. So if there in the cars, if we add only water to the car radiators, what will happen? Water will get freeze. Okay, so when it will freeze, what will happen? It will expand, and when it will expand, it will explode. Okay, so that's why we do not use only water in that places. We use a mixture of water and say any antifreeze solution, like any solute, say not any, they may must have some criteria. Okay, so one of such antifreeze solution is ethylene glycol in water. So if we take ethylene glycol and water, so what will happen? Water will not freeze at 0 degrees Celsius, rather the solution will freeze at, now it will freeze at minus 36 degrees Celsius, because we are adding ethylene glycol to the water. Okay, so now what will happen? The water will not easily freeze at 0 degrees Celsius. Okay, and hence we can easily use such type of antifreeze solution in the cars in places where there is the temperature is very very low as 0 degree Celsius. Okay, so from this you can understand why it is very important, why it is such a important criteria for us to know, right? So it is a day to day application. Now, as you know that the depression in freezing point is a colligative property, it will obviously depend upon the number of the solute molecules present in the solution, right? So that means what? You can see delta TF is directly proportional to the molality of the solution again. Okay, and when we remove the proportionality sign, we will get a constant known as Kf, and here it is known as the molal depression constant or the molal cryoscopic constant. So you have to remember Kb and Kf. So Kb, what is ebullioscopic constant, and Kf is cryoscopic constant. So definitions, it will be your homework, and the units, okay, for both. Now you can just the molality formula you will use here. Okay, simple molality formula, and you will get the final expression like this. So this expression will be used for your numerical point of view. Okay, and already I have told you the derivation, they never ask you. Okay, so the graph you can see, the definitions are important, and the final expression is important for doing your numerical, this one. Okay, so this was all about the depression in freezing point temperature. Okay, so I hope it is clear. In the next class I'll solve one problem so that it will be more clear to you how to approach the problem. Okay, so I'll end up here. So the third colligative property is over. We will take the fourth one in the next lecture. Thank you.